Hello, everyone. Okay, exams are just around the corner, right? So today we're going to do a super quick, super powerful revision on a topic that I can almost guarantee will come out, and that is radioactivity.
Have you ever really thought about it? How can scientists look at a dinosaur bone and say, yep, this is 65 million years old? Or how can doctors use something we can't even see to fight something as serious as cancer? Well, the answer to both, it's all about radioactivity. And that's exactly what we're going to master in the next few minutes.
So, we're going to go on a little journey today. We'll start from the very beginning, who discovered it, then we'll jump into the calculations you need for your exams, and finally, we'll see how all this science is used in the real world. I promise, by the end of this, you'll feel so much more confident to answer any question on this topic. So, are you ready? Let's go!
Okay, first things first. What exactly is radioactivity? Well, to understand it, we need to zoom right into the heart of an atom, into something called the nucleus. And it's all about what happens when that nucleus is, well, a bit unstable.
Okay, this definition has two super important keywords you must remember for your exam. The first one is spontaneous. Spontaneous just means it happens by itself. No one needs to push it or heat it up, it just happens. The second word is random. This means we can never, ever predict which exact atom is going to decay next. It's like popping popcorn, you know? You know they will pop, but you don't know which kernel is next. So it's a random, spontaneous process where an unstable nucleus just wants to calm down by releasing some energy.
And this whole process has a name: radioactive decay. I love this analogy. Think of an unstable nucleus like it's had way too much coffee. It's super jittery, full of energy, right? To chill out, it has to get rid of that extra energy. And it does this by shooting out radiation. After it does that, it's much more stable, much calmer.
So who were the brilliant minds who figured all this stuff out? Let's meet the pioneers of radioactivity. And listen up, guys, these names often pop up in exams, so it's good to know who's who.
All this happened in a crazy short amount of time, right at the end of the 1800s. It starts in 1895. Wilhelm Röntgen accidentally discovers X-rays. Boom. 1 year later, Henri Becquerel is working with some uranium compounds and finds they leave a mark on a photoplate even when it's wrapped up in the dark. He knew something weird was going on. Then comes the power couple, Marie and Pierre Curie. They take Becquerel's discovery and run with it, isolating not one, but two new super radioactive elements, polonium and radium. Can you imagine? What a time to be a scientist.
Okay, now we've reached a really, really important part of the chapter. This is where a lot of the marks are, When that unstable atom decays, it spits out radiation. But it's not all the same. There are three main types you absolutely have to know: alpha, beta, and gamma. Let's look at them one by one.
Let's put them side by side. First up, we have alpha. Think of an alpha particle as a bowling ball. It's big, it's heavy, it's actually a helium nucleus, and it has a positive charge. Because it's so big, it has a really high ionizing power. That just means it's really good at crashing into other atoms and knocking their electrons out. It's a real troublemaker. Then you have beta. Beta is more like a tiny, fast-moving bullet. It's just a high-speed electron, so it's much smaller and has a negative charge. And finally, gamma. Gamma isn't even a particle, it's pure energy, like a laser beam. No mass, no charge, just a pure energy wave.
So, because they're so different, their ability to pass through stuff, what we call penetrating power, is also very different. That big, heavy alpha particle, the bowling ball, it's so clumsy it can be stopped by just a single piece of paper. That's it. The beta particle, our little electron bullet, is a bit stronger. It can go through paper, no problem, but it gets stopped by a few millimeters of aluminum. But gamma? Oh, gamma is the real superstar of penetration. That laser beam of energy goes right through paper, right through aluminum. You need a really thick block of lead, like 10 centimeters thick, to stop it.
All right, everyone, take a deep breath. We're moving on to the calculation part. I know, some of you get scared when you see numbers, but trust me, half-life is one of the easiest calculations you'll do in physics if you just understand the concept. It's a guaranteed question, so let's make sure we can nail it.
So what is half-life? The definition is right there, but let me break it down. It's just the time it takes for half of the radioactive nuclei to decay. That's it. Let's say you start with 100 grams of a substance. After one half-life, how much is left? 50 grams. After a second half-life, how much is left? Half of 50, which is 25 grams. Then 12.5, and so on. See? It's a very predictable pattern.
Okay, let's try a real exam-style question together.
Don't panic, just follow the steps. We start with 32 grams of protactinium-234. The question tells us its half-life is 5.2 hours. We want to know how much is left after 20.8 hours. So, step 1, find out how many half-lives have passed. Easy. Just take the total time, 20.8 hours, and divide it by the half-life, 5.2 hours. You'll get exactly 4, so 4 half-lives. Step 2, just take the starting mass and divide it by 2 4 times. So we start with 32, after one half-life it becomes 16. After the second, it becomes 8, third, it becomes 4, and after the fourth half-life, it becomes
2 grams. That's it. See? Not so hard, right? As long as you follow these 2 simple steps, find the number of half-lives, then just keep dividing by 2. You will get the answer right every single time.
Okay, so we've done the heavy theory, we've done the math, now for the fun part. Why should we even care about all this? Well, it turns out radioactivity is used everywhere, in some really amazing ways that might surprise you.
First up, medicine. This is a huge one. For treating cancer, doctors can use a very focused beam of gamma rays from something like cobalt-60. Remember how penetrating gamma is? They can aim it right at a tumor deep inside the body to kill the cancer cells. It's also used for diagnosis. Doctors can inject a tiny amount of a radioactive substance with a short half-life, like sodium-24, into your blood. As it travels around your body, it acts like a little GPS tracker, and a detector outside can see if there are any blockages, like a blood clot.
And then there's archaeology. This is the super cool stuff. Remember how half-life is predictable? Well, all living things have a certain amount of carbon-14 in them. When they die, that carbon-14 starts to decay. By measuring how much is left, scientists can work backwards and figure out how old a fossil is. It's like a scientific time machine. And in factories, they use beta radiation to check the thickness of things like paper or aluminum foil. A source shoots beta particles through the sheet to a detector on the other side. If the sheet is too thick, fewer particles get through, and the machine adjusts itself. So clever, right?
And it's even in our food and farming. Farmers can use tracers like phosphorus-32 to see how well their plants are taking up fertilizer from the soil so they don't waste any. And this one you might have even seen, food preservation. Some foods are exposed to gamma rays to kill off all the bacteria. This makes them last much longer on the shelf. If you ever see this green logo, the Radura, that's what it means. And don't worry, it doesn't make the food radioactive at all.
Okay, we've talked about all the good things. But, like Spider-Man's uncle said, with great power comes great responsibility. Radiation can be dangerous if not handled properly, because it can damage our body's cells. So, there are very, very strict safety rules.
So, what are these precautions? Well, first, radioactive sources must be kept in thick lead boxes. Why lead? Because remember, lead is great at stopping radiation, especially gamma. Second, you never handle them with your bare hands. Scientists use robotic arms or long tongs to keep a safe distance. And third, anyone who works near radiation has to wear a special badge called a dosimeter. This badge measures how much radiation they've been exposed to over time, just to make sure they're always safe.
Now, this is one of those numbers that's good to remember for your exam, just in case. The safe level of background radiation for the public is considered to be less than 0.2 microsieverts per hour. It's just a safety benchmark that authorities use.
And there you have it. That's our quick revision of radioactivity. We've gone from the discovery to the 3 types of radiation, we smashed that half-life calculation, and we've seen all the amazing uses and the important safety rules. You guys now have the core knowledge you need.
So I want to leave you with a final question to think about. We've seen that this science is so powerful. It can heal us, but it can also be dangerous. It's a real double-edged sword. So my question to you is, what's next? What do you think the next big breakthrough using radioactivity will be? Maybe in energy or space travel. Let that thought spark your imagination. Thanks for watching, everyone, and all the best for your studies.